The phenomenon where hot water can freeze faster than cold water is known as the Mpemba effect, named after Tanzanian student Erasto Mpemba. Despite its counterintuitive nature, several hypotheses have been proposed to explain this effect. When hot water is exposed to freezing conditions, it loses a significant amount of water through evaporation. This reduces the overall volume of water that needs to be frozen. Since there's less water to freeze, the remaining water can freeze more quickly. Evaporation also removes heat from the water, accelerating the cooling process. Hot water sets up more vigorous convection currents than cold water. Convection currents are the circular movements of fluid caused by the rising of warmer, less dense fluid and the sinking of cooler, denser fluid. These currents help distribute the heat more evenly throughout the water, leading to a more uniform cooling and potentially quicker freezing. Supercooling occurs when water is cooled below its freezing point without forming ice. Cold water is more likely to supercool than hot water because it lacks the disturbances necessary to initiate the formation of ice crystals. Hot water, as it cools down, passes through the temperature range where ice nucleation is more likely to occur, reducing the chances of supercooling and allowing it to freeze faster. Hot water tends to lose dissolved gases more rapidly than cold water when heated. These gases can affect the freezing process. Water with fewer dissolved gases has a different structure and can freeze more quickly. As the hot water cools, it has already expelled many of these gases, potentially leading to a faster transition to ice. Impurities in the water can lower its freezing point, a phenomenon known as freezing point depression. Hot water may initially have a higher concentration of impurities due to dissolved minerals and gases. The Mpemba effect is still a subject of scientific debate, and no single explanation accounts for all observations of this phenomenon. It is likely that a combination of factors, including evaporation, convection currents, supercooling, dissolved gases, temperature gradient, freezing point depression, and container effects, contribute to hot water freezing faster than cold water under certain conditions. The precise conditions and relative importance of each factor can vary, making this an interesting and complex topic in the study of thermodynamics and fluid dynamics.